leads to fuel properties that can vary considerably too. So biodiesel from palm oil can be very different from a biodiesel made from algae or from soy or from some other feedstock. Next slide, please. So how do you make biodiesel? I assume most of you know that anyway. It's been talked about this morning too. Essentially, you want to make a less viscous fuel, because if you compare the so-called kinematic viscosity of a vegetable oil and that of biodiesel, you'll see that biodiesel has a lot less kinematic viscosity, reduced kinematic viscosity, which is closer to that of petroleum diesel that you usually use. That's derived from petroleum. Byproduct, talk about that, was glycerol. Biodiesel production. A few words on the reaction itself. Stoichiometrically, you need 3 moles of alcohol to make biodiesel, but you should use 6 moles of alcohol and should stick that as closely as possible. Just like the sensitivity to water and those things that have been mentioned are fatty acids, the reaction is also very sensitive to the molar ratio. If you don't have enough catalyst or you have too much catalyst, that can lead to a problem too. Next slide, please. So what actually is that stuff that's in the biodiesel? The major components, the methyl esters of fatty acids. Usually you use methanol to make biodiesel. Alcohol, other alcohols will work too. I'll be talking about that a little bit later in my presentation. But anyway, what we might call the 5 classical fatty acids are methyl palmitate, methyl stearate, methyl oleate, methyl linoleate, methyl linolinate. There are 2 saturated fatty acids up there in these classical 5, methyl palmitate and methyl stearate. Their structural formulas are somewhat abbreviated up there next to them. There's a methyl oleate, which has 1 double bond in the chain. So it's in the monounsaturated fatty acids, methyl linoleate, doubly unsaturated, and methyl linolinate, triply unsaturated. And these structural differences lead to different properties. I'll be talking about that. Then from other oils, we can get, for example, methyl laurate in biodiesel. If you use coconut oil, some tropical oil that usually have shorter chain fatty acids, you'll see that methyl laurate has less CH2 groups in the chain. Castor oil can give you methyl ricinoleate. Its major feature is that it has an OH group at one of the carbons of the chain compared to methyl oleate. And then from algal oils, you can get what you might call highly polyunsaturated fatty acid methyl esters, like methyl icosapentaenoate or methyl docosahexaenoate. It's even more carbon atoms in the chain, but a lot of unsaturation. Next slide, please. That are, of course, the major components in biodiesel that are desired. And actually, in the first 2 presentations this morning, that was discussed a lot too. There are minor constituents in biodiesel that can cause a lot of problems. They can influence properties like cold flow, the oxidative stability, corrosion, combustion. Some of them might be even catalyst poisons if you're using a catalytic exhaust system, or can influence lubricity. Lubricity might actually be positively influenced by some of them. But anyway, I think we talked about that. Triacylglycerols, diacylglycerols, monoacylglycerols. I think Ray mentioned essentially when you're chopping off a finger off the E, you get the di and monoacylglycerols. So that can be present in biodiesel. Then obviously some glycerol as the co-product of biodiesel production, the free fatty acids. Talked about that, the alcohol you use for making biodiesel production. Then there are 6 heteroelements that are limited in biodiesel standards: sodium, potassium, calcium, magnesium, phosphorus, and sulfur. You find them in biodiesel. They might be just carryovers from the feedstock, or from contact with extraneous materials, or from the catalyst. For example, if you're using potassium hydroxide, you might get some potassium in there, or something like that. And then there are the infamous duroglucosides, which essentially kind of are present in the feedstock but are transformed during the trans-esterification reaction. Their problem is that they also have high melting points. Next slide, please. So technical problems with biodiesel have been traditionally cold flow. That biodiesel might not flow or at cold temperatures, or when you cool it down, let's say to a temperature around 0 degrees Celsius or 32 Fahrenheit, that you'll see crystals form. Obviously, that can clog fuel filters, things like that. The fuel might not even get to the engine. Oxidative stability. Biodiesel is known to be sensitive to contact with air due to some of the unsaturated fatty acids present there. I'll be talking about that a little bit later too. Then there's the issue of nitrogen oxides, exhaust emissions. I think that has come up this morning again too a little bit. Although that issue may fade somewhat with time because of new exhaust emissions control technologies, because essentially everything you put in the diesel engine will be then kind of after treated by the catalytic system that's in the exhaust. Then, as I talked about, minor components can influence these fuel properties too. Usually reduced oxidative stability or cold flow, for example. Next slide, please. So this is the biodiesel standard ASTM D675111A. It changes about 2 or 3 times per year, but anyway, it's fairly extensive. Some of the issues I talked about, I'm going to go through that in detail. Next slide, please. And then there's the European standard EN 14214, kind of the analog used in Europe. It's, I think, important to be aware of both of them. Obviously, in this country, D6751. But if you're getting to business, let's say, abroad, you really have to be aware of EN 14214, because a lot of people look at EN 14214-2. Actually, some biodiesel standards in other countries around the world have used not only ASTM D6751, but EN 14214-2 as guidelines as what they're going to put into their standards. Next slide, please. So now I'm going to go a little bit back to fatty acids after this excursion into the standards. Some typical fatty acid profiles for some more common commodity oils, and one of the alternatives, jatropha. You'll see that they vary a lot. I've got methyl palmitate up here, C16-0, methyl stearate, methyl oleate, C18-1, methyl linoleate, C18-2, and methyl linolenate, C18-3. You'll see that they can vary considerably depending on the feedstock, and as I mentioned, that will influence the fuel properties a lot. Next slide, please. So you see, for example, palm oil, which had about, let's say, roughly 45% of methyl palmitate, which has a very high melting point. So you'll see that it has a cloud point of about 16 degrees Celsius. Cloud point, the temperature at which the first solids or crystals form in a fuel when you cool it down. The other fuels didn't have that much of the methyl palmitate in there. You'll see that their cloud point is lower. They have less of the higher melting components. See that the cetane number, of course, kind of the diesel fuel analogous to the octane number, varies a lot depending on the fatty acid composition. You'll see that similar to what I mentioned about the historical studies on methyl esters of palm oil. See that methyl esters of palm oil have a very high cetane number, too, higher than that of most other diesel fuels too, biodiesel fuels too. Again, the influence of the fatty acid profile. Kinematic viscosity, I mentioned that. The major reason for making biodiesel, you'll see that these fuels, however, are all fairly close together in that respect. So, next slide, please. And now maybe a little bit of a synthesis on the standards and the fatty acid profiles. Go through the standards. There are actually different kinds of specifications, you could say. There are specifications that are inherent to the fatty esters that influence the biodiesel standards, the cetane number, the cold flow, viscosity, oxidative stability. They are directly related to the major components, which I'll be talking about. If you look in EN 14214, there are some feedstock restrictions. I won't get into that in detail, like iodine value. Viscosity is affected as specific esters. And then in some respects also density in EN 14214. So there are properties that are inherent to fatty esters that are in biodiesel standards. And then there are the properties or parameters that are related to production storage. Could be, as I mentioned, extraneous materials influencing the biodiesel carryover from the feedstock, like the acid value, the free and total glycerol, the 6 hetero elements, water, sediment, the sulfated ash, carbon residue. And then there are 2 issues that have always influenced biodiesel a lot, but you won't find them in any standard. Exhaust emissions, they're dealt with by essentially regulations set, for example, in this country through the EPA, through legislative authority. And then there's the issue of lubricity. You won't find that in any biodiesel standard, so you look at the Petrodiesel standard for that. So, next slide, please. I'll be getting closer to the fuel properties of fatty esters. General observation, if you recall the structures I had up there, the chain length, the number of CH2 groups in a fatty acid chain influence of the fuel properties, and the number of position of double bond in a fatty acid chain will influence the fuel properties. So I think it's important to keep these 2 general observations in mind if you're looking at fuel properties of fatty esters. Next slide, please. I'll start out with the cetane number. I had that in this little historical excursion. We talked about it at some other occasions. So it's kind of conceptually similar to the octane number of gasoline, except that it relates to diesel fuels, or you might call it dimensionless descriptor, related to the ignition delay time of a fuel in a cylinder. Generally, the higher the cetane number, you could say the better the combustion, put it that way. And hexadecane, which is essentially a hydrocarbon with 16 carbon atoms in the chain, straight chain compound, is a high quality reference compound. It has an assigned cetane number of 100, and that's also, by the way, why the cetane number is called cetane number. Hexadecane is a systematic name for the compound, and it also has a trivial name called the cetane. So it's essentially identical to this cetane and the cetane number. One issue that has been raised in the past is that the cetane number can, to some extent, be correlated to NOx exhaust emissions. Generally, saturated compounds that have a higher cetane number, as we'll talk about, show reduced exhaust emissions. So some people have correlated that to the cetane number. Exercise some caution when doing that, but that's another matter. Next slide, please. So, if you look at cetane numbers of neat compounds, like the fatty esters that are in biodiesel, I hope everybody can read that. But you'll find that saturated compounds like methylpalmitate up there, C16.0 and C18.0, they have very high cetane numbers, and they are above the limits in the biodiesel standards, which are 47 and E67, 51 and 51 and EN 14.214. You'll see that, for example, methyl oleate, the C18 carbon, essentially with one double bond in the chain, also has a cetane number above the specifications. Well, 2 of the other common components in biodiesel, the C18.2 and the C18.3, the methyl linoleate and methyl linolenate, are actually below the specifications. So to get a biodiesel that meets specifications, obviously you have to have compounds, higher cetane compounds that can compensate for the cetane numbers of lower cetane compounds. I've also got up here in kind of this brown color, two components that you can find in some algal biodiesel fuels, the C20:4 and C22:6. Now you might recall that I mentioned C22:5 as a component of algal oils. We did not cetane test that because it was just too expensive to get, so we just took C20:4. But we were able to investigate C22:6, and we find that they too have very low cetane numbers, generally because of that high unsaturation, similar to the C18:3. Next slide, please. So, anyway, as I mentioned, the cetane number of a mixture is essentially just taking the components and their cetane numbers proportionally and adding them up, and you'll get this cetane number of a mixture. So that's why components with high cetane numbers will compensate for those with a lower cetane number in a mixture of fatty acids that make a biodiesel. And as I mentioned, most biodiesel from vegetable oils will meet the cetane number requirements and standards because there are sufficient amounts of these esters with a higher CN. Yes?
Yes. The oils with the fatty acid profiles include the C18, C20, C22s that are below the cetane number. What are the most common oils that you're seeing that's other than algal you mentioned?
With the cetane numbers below? Well, probably the most prominent one you could think of would be linseed oil, which has a lot of C18:3.
Maybe flax or canola.
Yeah. Canola actually does pretty well because it's essentially kind of the high oleic version of rapeseed oil. But rapeseed oil itself will actually do pretty well too. If you're thinking hyalusic, if you can go back a slide. I didn't show it here, but the C22:1 in hyalusic rapeseed is that dot up here. So it actually has a fairly high cetane number because of its fairly long chain, so there's no problem there. So like I said, probably the most prominent one that's not algal that will have a problem cetane number because of high unsaturated will probably be linseed oil.
Okay.
Yeah.
There are fish oils perhaps as well?
Fish oils too, yeah. Maybe you can generalize marine oils instead of algal oils, yeah.
And isn't there a variety of soy that's high in linoleic that's sometimes borderline with...
Linoleic, yeah. Well, that's essentially why the cetane number of in the ASTM specification is set lower in EN 14-14 because cetane number of soy methyl esters is a little bit lower than that of what the Europeans call rapeseed. What the Europeans call rapeseed is essentially canola.
Right.
So, and it has you could say between what the Europeans call rapeseed or canola and soy, the C18:1 and C18:2 are roughly reversed. So rapeseed or canola has a little bit higher C18:1 with higher cetane number, so overall cetane number is higher. That's essentially why they set the higher cetane number, otherwise it's a little bit lower in 6751. And I think pretty much you could say ASTM 6751 is set at 47 minimum. Most soy usually comes in at least a little bit higher than 47, so it'll allow soy.
Since you have that slide up, what would C14 be, myristic acid?
Methyl myristate, I don't think we ever tested that, but it would probably, that's C10, that's C12, that's C16, so you could probably do a linear interpolation between the C12 and the C16. So, I didn't put that up there. It's fairly rare in most vegetable oils. Yeah. Yes.
Have you done any testing with algae-based biofuel oils yet?
I'd love to, if you can get it. Yeah, because we've actually tried, and I mean, to be honest, try to get it is almost impossible. I mean, and you read a lot of reports out there. You think, oh, it shouldn't be a problem if you try to get it. It's impossible. Next slide, please. And we've been there, so another slide. And actually, you can use the cetane number to discuss or explain the question is why we use triacylglycerol feedstocks or vegetable oils as feedstocks for making a diesel fuel. So if you go back and look at the structure of hexadecane, I mentioned it's a long hydrocarbon chain. And you look at the structure of fatty esters, like in biodiesel, you see that they have a long hydrocarbon chain too. Well, the only difference being that's the first carbon, where biodiesel has a methyl ester group, and hexadecane obviously has the methyl ester group too at the first carbon, but otherwise they have this long hydrocarbon chain. So the structural similarity is the reason why you can use something like biodiesel as an alternative in a diesel engine. Next slide, please. Now, since we talked about cetane number, that's a little combustion-related stuff, I'll say a few words about exhaust emissions. Now, this is an older US EPA report from about 2002, where they had looked at exhaust emissions from various studies in the technical literature, and kind of, could say, combined and averaged the results, and compared biodiesel to petroleum diesel in terms of the 4 regulated exhaust emission species. The 4 regulated exhaust emission species are NOx, nitrogen oxides, particulate matter, carbon monoxide, and hydrocarbons. And just to put it that way, NOx and particulate matter are probably the 2 that people care most about. And if you look at neat biodiesel versus petroleum diesel, you see the little bit of the NOx penalty that biodiesel has, but it has advantages in terms of the other 3 regulated exhaust emissions, most notably in terms of the particulate matter. Now, if you prepare blends of biodiesel with petroleum diesel, you'll see that the effect is roughly linear to the blend level. Here's some the data for B20 the US EPA had in their report. So you'll see that NOx penalties are reduced, but the benefits in terms of the other 3 exhaust emission species are reduced when you're using the B20. Next slide, please.
Question.
Yes.
I understand that was one of the issues with biodiesel, and the NBB even went forward and said, hey, we think this study is old. Have they redone that study, particularly in regard to NOx? Yeah,
well, actually, as far as I remember, Bob McCormick and ENRA has done that and shown that there's probably not that much of a NOx effect. So you might have heard about that.
Yes.
Yeah, that's what you're referring to, yeah. So, nevertheless, you'll still find in the literature lots of reports about the NOx issue with biodiesel. Actually, we've done some work in conjunction with the Southwest Research Institute and did see an effect on NOx too. So, and as I mentioned on one of my earlier slides, the issue is, let's say with newer engines that have newer exhaust emissions control technologies, will the issue fade with time? So, of course, most diesel engines have a long lifespan, so let's say engines that were built in the 1990s or something like that, or early 2000s, that may not meet those specifications, but will be on the road for a while. So,
how much does the feedstock affect the NOx?
Actually, I'll be talking about that a little bit in the next few slides. I mentioned that we had also done some work in conjunction with Southwest Research Institute, and tested some, actually this was technical grade methyl oleate. It was not really pure stuff, it was about 77% pure. But also some methyl palmitate and methyl laurate, which are the saturated C12 and C16 fatty esters, and compared them not only to a commercial biodiesel, a soy biodiesel here, but also to a petroleum biodiesel fuel, and also to hexadecane and dodecane, which are obviously the straight hydrocarbon chains. And hexadecane, of course, being the high quality reference compound on the cetane scale. Dodecane just a little bit shorter and elegant. Was also interesting to compare these neat compounds, these neat hydrocarbons, and the neat to the fatty acid methyl esters is in the so-called renewable diesel that you can make from, for example, vegetable oil feedstocks. They should be enriched in, for example, hexadecane and dodecane in straight chain hydrocarbons and saturated hydrocarbons. So anyway, you'll see an effect again here on NOx and particulate matter, the two major species everybody worries about. You'll see a little bit of an effect of NOx of the soy biodiesel and the methyl oleate, increasing it slightly compared to the petroleum diesel fuel. But you'll see that essentially the other fuels, including the methyl palmitate and the methyl laurate, which are saturated fatty esters, actually lowered the NOx a little bit, but not quite as much as did the hexadecane and dodecane. But anyway, you'll see that essentially, relating that a little bit to the cetane number issue, the higher cetane compounds, the saturated compounds generally do a little bit better in terms of NOx. Also relating that to the two issues of the EPA study and the Bob McCormick study is, yes, you can to some extent observe the NOx effect. Like I said, with the new exhaust emissions control technologies, it might become less of an issue. Well, you'll see that biodiesel did exceedingly well in terms of particulate matter. Actually, did even a lot better than the neat hydrocarbons. Next slide, please. So if you do it in terms of percentages, if you kind of set the petroleum diesel to 0 and relate the other fuels to the petroleum diesel, you see the effect of the methyl soyate and the methyl oleate, the slight increase on the NOx. You'll see that the oleate actually did better than the soyate. The reason probably is the technical grade methyl oleate we used was 77% pure. There was some other fatty ester components. So overall, unsaturation was probably lower than the methyl soyate. And you do see the little bit of benefit of the methyl palmitate and the laurate versus the petroleum diesel fuel. But not quite as great as it is with hexadecane and dodecane for the NOx. But then you do see the, I call almost dramatic effect on the particulate matter exhaust emissions, essentially for all the biodiesel fuels and their components tested. So, next slide, please. Talk a little bit on NOx and particulate matter, pointing out that they are probably the two species people care most about. I don't want to forget the hydrocarbons and the carbon monoxide. These were the effects here. You can see some effect of chain length here too, and also of the biodiesel being probably more unsaturated than the hexadecane and dodecane. Something else, we've been talking about chain length and unsaturation effect on exhaust emissions. You might notice too that the group at carbon 1 in the chain has an effect too on the exhaust emissions. Otherwise, for example, you wouldn't see the differences, for example, in carbon monoxide, looking at dodecane and methyl laurate. You'll see these differences here too. So obviously there's an effect on the methyl ester group versus the methyl group in the first carbon too. So next slide, please.
Can you just quickly say again where canola-based biodiesels fit in there again?
Canola, it would probably be somewhere between methyl soyate and methyl oleate in this case. Since that was about 77% pure methyl oleate in the technical grade with some other stuff. Let's say if the canola, or what the Europeans call rapeseed, is let's say 55% methyl oleate. So we'll probably, like I said, somewhere in between the methyl soyate, which has, let's say, 25% methyl oleate. So somewhere in between there. Okay, next slide, please. I'll say a few words about viscosity. Since that's essentially the major reason why you make biodiesel in the first place. Again, as compared to, as I've done with the Cetane number, I put in the specifications here too. The gray bars are the range that ASTM EP6751 allows for a biodiesel fuel. The blue bars indicate what EN 14214 allows. And of course the symbols in between the ranges mean that these components would not cause the biodiesel to violate or let's say not meet the specifications for viscosity. Now it works out that essentially most major biodiesel components, like methyl palmitate, methyl oleate, and even the methyl linoleate, have viscosity in the range between 3.5 and 5.0, which is the European range. ASTM 6751 is more generous. It goes between 1.9 and 6.0. So essentially, it pretty much allows all potential biodiesel components for using a biodiesel fuel. So you'll notice that essentially EN 14214 has a very narrow range. You could say that's actually a little bit of a feedstock restriction. It would, for example, exclude some tropical oils like coconut oil, which have a lot of C12. You'll see that the viscosity range is below the lower limit in EN 14214. So that's a bit of a feedstock restriction, probably in EN 14242, to guard the rapeseed / canola oil. Well, like I said, ASTM 6751 is pretty generous. So you can use a lot of feedstocks and not run afoul of the viscosity specification. Next slide, please. Just a few more words. You can observe an effect similar to other properties. It depends on chain length and increasing saturation. And the kinematic viscosity of a mixture of fatty esters is essentially proportional to the components and their amounts. As I mentioned, unfortunately, all biodiesel fuels meet ASTM 6751. EN 14214 is a little bit more restrictive. Next slide, please. So here, cold flow, essentially melting points of fatty acid esters. In red, you have the saturated methyl esters, the major components of biodiesel, and for comparison here, actually ethyl esters, you'll see that ethyl esters do actually a little bit better in terms of cold flow. Their melting points are a little bit lower. You see that the melting point of methyl palmitate here is 28.5 Celsius, and that of methyl stearate, the C18 is about 37.7 degrees Celsius. That's obviously the major reason why they can cause cold flow problems. That's actually well above temperature, room temperature. Unsaturation, of course, lowers the melting point considerably. For example, methyl oleate, the C18-1, has a melting point of minus 20.2, and the two other, or called the classical fatty esters, are C18-2 at about minus 43. And the 18-3, I just put the symbol there, but it's actually well below 50. It can, some sources say it's 52, it might even, minus 52 can be even lower. Might be worthwhile noting, I don't have any data here for the highly polyunsaturated fatty esters like you can find in the algal or fish oils. They'll probably be off the chart here, so probably even below the C18-3. So. One of you asked about rusic acid or methyl rusate. And biodiesel is up there. That's about minus 3.1. And then I've added another compound here, methyl oleate, which is a C16 compound with one double bond in the chain. Has a melting point of minus 34. And I put that up there because I think that's a potentially interesting compound to enrich in biodiesel. So next slide, please. So again, similar to other properties, cold flow depends on chain length and unsaturation. The cold flow properties are determined by the nature and amount of saturated compounds. Now, in contrast to viscosity and cetane number, I'm going to bring up a nice little equation here because cold flow does not work that way. For viscosity and cetane number, you can just take essentially the compounds and their amounts and just add them up proportionally, and you'll get very good approximations. Does not work that way for cold flow. Mentioned the cloud point for some neat fuels some slides ago. What I showed here was, of course, melting points. That was for pure compounds. The cloud point, keep in mind, of course, is for a mixture. So, obviously a mixture, the components have different melting points, and they will start to crystallize at different temperatures depending on their amounts and maybe what the other components are. That's why you essentially get kind of like a crystallization range, or if you heat it up again, a melting range. That's why you use a cloud point. First temperature, at the first temperature which you can see crystals or solids form in the fuel. It's a little bit soft specification biodiesel standards. ASTM 6751 calls for a report. So obviously the cold flow requirements in Minnesota in winter and not maybe the summer are quite different than year-round, let's say in Arizona or even here in Southern California. So there's something else that addresses cold flow too now, but that's more for long-term storage in ASTM 6751 called cold soak filtration. EN 14214, instead of cloud point, uses a so-called cold filter plugging point, and it's a soft thing too because it depends on time of year and geographic location. And overall, probably the cloud point is more stringent than the CFPP. Next slide, please. And how we have to keep in mind for cold flow is that the minor constituents, such as monoacylglycerols like monopalmitin, monostearin, and seroglucosides, have a significant influence on cold flow. For example, melting points of monopalmitin, monostearin are about 70 degrees Celsius. The seroglucosides are around 240 Celsius. And one of the nasty little things is that these effects are often noticeable upon prolonged storage. Let's say if you make the biodiesel fuel fairly freshly on your cloud point, you might get a good cloud point, but you store it for a while. Suddenly you have this precipitate there, and your nice cloud point has gone up. So, okay. Yes?
How long is that period? I mean, is that a year? Is that 2 years? Is that 3 weeks?
That depends. I mean, it can depend on the feedstock that was used for the biodiesel, the temperature it was stored at, also, let's say, the overall quality of the fuel. So, let's say if you had a transesterification reaction that didn't quite go as well as it did, might have a little bit more monopollent and monosterin, that can affect it too. So there are lots of parameters that can affect it. And I would not put a timeline on that for that reason, because there are so many factors that can affect it. So you just look at it and you'll notice it. So okay, next slide, please. Other big issue with biodiesel that can be traced largely to its major components is oxidative stability. And it's also just going back to the last question, it's also affected by a lot of parameters. For example, presence of air, temperature, light, extraneous materials, which could even be a container material, and even the headspace volume with which you store the biodiesel in the tank. So, structural reason for the oxidation of fatty compounds are called allylic and especially the so-called bisallylic CH2 positions you'll find in C18.1 and especially C18.2, C18.3. So C18.1 has essentially two allylic positions, essentially CH2s next to a double bond, but if you go to C18.2, the methyl and oleate, you'll find two allylic positions and one bisallylic position. At C18.3, you'll find two allylic positions and two bisallylic positions, essentially two CH2 sandwiched between double bonds. Next slide, please. And to put these semi-quantitatively, numerically, from some other literature, if you set a relative rate of oxidation of oleates to 1, you'll see that linoleates with two double bonds are a lot more reactive in oxidation, and the linates with three double bonds are even more reactive. While chains with three double bonds, for example, like you find in algal oils or fish oils, generally marine oils, have even higher relative rates of oxidation. They might go even above 200. So the question is, the oxidative stability of mixtures, like vegetable oil esters, directly proportional to the amount of unsaturated compounds, or do small amounts of unsaturated compounds have greater influence than their amounts indicates? And I think generally the answer to that question is yes. So it's a little bit similar to actually cold flow. If you have small amounts of these high melting components, they can screw up your cold flow too, and that can happen to your oxidative stability too. So next slide, please. So I assume that many or most of you are aware of the so-called ransomware test, which is used for assessing oxidative stability. It's prescribed in biodiesel standards. You have to run it at 110 degrees Celsius. That's a little bit of an issue too, because obviously 110 degrees Celsius is above all storage conditions. It's an accelerated test, because otherwise it will just obviously be too slow and might take you days or weeks. Generally, the higher the so-called ransomware time or induction time by that test, the better. For example, saturated esters will be about 24 hours, while methyl oleate, the C18.1, about 2.8 hours, while the C18.2, C18.3, you'll see the effect of the bisallylic positions in the chain. So they have very low times. By the way, similar for the C20:4 and C22:6, like the stuff you'll find in the algal oil, they have very low ransomware times too. If you compare that to ASTM D6751, it has a minimum specification of 3 hours, and EN 14214 6 hours. And considering that even smaller amounts of highly polyunsaturated compounds, or even, let's say, even the monounsaturated, may have more influence on oxidative stability than their amounts indicate. CAUR is always even antioxidant in your biodiesel to meet the specification, especially if you're storing it a long time. So some people have made a little bit of a deal out of the 3 hour versus 6 hour difference in D6751. EN 14-14, but if you look at the data here, considering that essentially all unsaturates are below the 3-hour specification anyway, it's probably not a big deal, my personal opinion. Anyway, next slide, please. I'm going to say a few words about density. It's really not that much of an issue. I'm just going to sneak it in because it's contained in EN 14-14. I think mainly as a reason to exclude the vegetable oils from fuel use because their density is higher than that of the biodiesel. The only point where it might be a problem for some biodiesel fuels is like in algal oils with the highly polyunsaturated fatty acid methyl ester, which have a density higher than that prescribed in EN 14-14. But you'll need fairly high amounts of those in the algal oils to exceed the specification. And again, the density can probably be calculated similar to viscosity and cetane numbers just from the compounds and their amounts. Next slide, please. A few words about lubricity. Biodiesel has excellent lubricity. Because that had been a reason in the past, a technical reason for promoting the so-called B2 biodiesel blends, because you get lubricity benefits if you add about 2% biodiesel into the low lubricity ultra sulfur diesel fuels with marginal cost impact. I mentioned previously it's not included in biodiesel standards, so you use this method here that's in Petrodiesel standards with a so-called maximum wear scar generated on a steel ball. Next slide, please. Might be actually interesting to note that in terms of improving fuel properties or not improving fuel properties by contaminant, lubricity is actually improved by some of the minor constituents on contaminants in biodiesel. So, for example, we tested a ULSD ultra-low sulfur diesel fuel with these wear scars, which exceeded specification of petroleum diesel standards. You put in 1% methyl oleate neat. It improved the wear scar a little bit, but not that much to meet the specifications. You put in 1% oleic acid, the free fatty acid of methyl oleate, and put 1% of that into ULSD fuel, so essentially you have 0.01% of oleic acid, 1,000 ppm. Then the ULSD fuel and the wear scar increases incredibly. So, on the other hand, if you put in 2% methyl oleate, you do see the positive effect of putting in more methyl oleate compared to the 1%. Got an acceptable wear scar here. Next slide, please. And just for sake of completion, you might note that there is some effect of chain length and unsaturation on lubricity. Generally, the wear scar improves with the increasing number of double bonds and greater chain length compared to it. You'll notice that actually free fatty acids probably do the best in terms of lubricity. I've got that down here as COH. And some other oxygenated so-called functional groups are actually better than methyl esters. Next slide, please. Summarizing a little bit of what I've talked about, there's also a property trade-off. If you increase the chain length, you get a higher melting point, which is a negative because it can negatively affect your cold flow properties. If you increase the chain length, you get a higher cetane number, obviously a positive, and with some accompanying maybe positive effects on some exhaust emissions. So, increasing unsaturation, you lower the melting point, which is nice for cold flow, but you decrease the oxidative stability and the cetane number. So that has been one of the quandaries of biodiesel trying to improve these properties, because improving one might actually worsen the other. So, next slide, please. So overall, you could say there are about 5 approaches to improving biodiesel fuel properties. One is just using additives. You have unchanged fatty ester compositions. I'm not going to talk about that very much. Then essentially you can have a modified fatty ester composition. And I actually need fatty ester here too, because obviously when you're making biodiesel, you're taking two components to make biodiesel, the acid and the alcohol. So you can change the alcohol too. So change the fatty acid profile, there are physical procedures. Or you can have an inherently different fatty acid profile, either through using alternative feedstocks or a genetic modification of existing feedstocks. Next slide, please. Then I'm not going to talk about additives, since I'm dealing mainly with the properties of fatty esters here. Additives, you have, for example, cold flow improvers, or heard about 4-point improvers. But they often really do not affect the cloud point that much. So we can improve the core point, that's an issue with them. Then there are antioxidants. I think I mentioned that when I talked about oxidative stability. Keep in mind that they're not a cure-all either, because they're actually oxidation delayers and not preventers. So once essentially the antioxidants have been used up, then the oxidation of the biodiesel will set in. So I will not talk about that too much either. Physical procedures, for example, winterization for removing saturates. Downside is, of course, you're removing the compounds that are better for combustion by enriching the unsaturates. It does have its positive effect on cold flow, but like I said, it also has its downside. Next slide, please. I'll say a few words about the influence of the alcohol moiety. I pointed out you can change the fatty ester composition. And you'll recall that on the data I showed for the melting points of neat fatty esters, that the ethyl esters had lower melting points than methyl esters. You'll see that here too. If you compare, for example, BC16 esters here, so the larger the alcohol to about C4, C5, the lower the melting point. It starts to reverse at about C5, C6 again. But you use some alcohol, for example, ethanol or propanol or isopropanol, you get biodiesel fuel that has probably improved fuel properties. No negative effect on cetane number, maybe even positive because of greater CH2 groups. So viscosity is a little bit higher, but probably not out of spec, especially for D6751. The major disadvantage is the higher cost of the alcohol, and also the issue that when you use ethanol or propanol or some other alcohol instead of methanol, there's a tendency for the transesterification reaction to form emulsions that the two phases you get will not separate that easily. Next slide, please. I had mentioned that, but you can gather from the other data I presented that probably oleic acid, C18-1, is probably the best compromised fatty acid to enrich among the classical 5 fatty acids. The biodiesel fuel, if you want to improve properties, its melting point is about -20. The cetane number is, yeah, you can say between 55 and 60. Oxidative stability, well, it doesn't meet the specifications, but it's not as bad as the polyunsaturates, so it's a good compromise among the 5 classical fatty acids to enrich. Question is there even something better than methyl oleate possible in biodiesel? Getting into chemistry, positional isomers, which means that the double bond is at some other position in the chain. There's really no major advantage to that, to most of them, either in terms of melting point or issues like that, as far as I can tell. Also, geometric isomers, cis-trans, heard a lot about trans fatty acids. That's essentially the same thing here. They're probably not an alternative either. They have higher melting points and higher viscosity. They're probably not much of an alternative either. Hydroxylated chains, I talked a little bit about methyl oleate. As you can refined castor oil has a high viscosity, low cetane number, oxidative stability. Probably not much of an alternative. Then that leaves two issues with shorter saturated chains and shorter unsaturated chains. Shorter saturated chains like C10, C12, fatty acids. Shorter unsaturated chains, I mentioned like methyl palmate oleate when I had one slide on the melting points of fatty esters. So, next slide, please. Anyway, for the shorter chain monounsaturates, I mentioned methyl palmate oleate. I think that if it ever could be enriched in a biodiesel fuel, it would probably be better than methyl oleate. Its melting point is -34, the Cetane number. And several tests has come in between 51 and 56, so it's acceptable. Viscosity is a little bit lower. Oxidative stability is a little bit lower too than that of methyl oleate. Not necessarily because it's more oxidatively unstable than methyl oleate, but that's a little bit of a quirk of the method. I'm not going to get into the details of that. Exhaust emission is probably similar to methyl oleate. Methyl oleate might even be better, but the Cetane number is probably going to be lower. It's fairly expensive to get, so no further data on that. So, next slide, please. Following up a little bit nutty idea, we looked at macadamia methyl esters because that's enriched in C16.1. Unfortunately, because it also contains some saturated compounds, its cloud point was not much better. So next slide, please. There we go. Shorter chain saturates. You'll see that their melting points are reduced compared to methyl palmitate or methyl stearate. If your chain gets a little bit too short, like C8, the Cetane number will fall off and meet those specifications. Point out that all have high oxidative stability too. So next slide, please. Actually, we're fortunate enough to have access to vegetable oil highly enriched in C10, a variety of Kufia, which has about 65% C10 fatty acid, and that compares to these feedstocks here, which are very different. These might call classical feedstocks. So, Kufia has only very little of this classical C16 to C18 fatty acids. And next slide, please. So you'll see that actually imparts some advantages to it. The Cetane number is still acceptable. Viscosity is fairly low, pretty much in the range of petroleum diesel fuel to meet the ASTM 6751 specification. So we'll probably still need an antioxidant, maybe not a surprise. But the cloud point was reduced to -10 to -10 Celsius. So that's, at least for, let's say, even some parts of this country, still a big deal, but maybe it don't cool down that much in winter. So, and it's obviously, compared to some biodiesel, about a 9 to 10 degrees Celsius improvement. Next slide, please. And we've had some collaboration with some individuals, Sandia and some others on that. Some we're excited about it because the properties are closer to that of petroleum diesel. If you look at the distillation curve of the Kufia methyl esters, you'll see that it starts similar to that of the petroleum diesel fuel. And only its major advantage, or so-called advantage, or alleged advantage, claimed high production potential, order of magnitude greater than the highest yielding vegetable oil in, let's say, the most optimistic assumptions. Also avoids the fuel versus fuel issue, but there have been some problems with growth and harvesting of algae and oil extraction. Production costs have been fairly high. Also, there's with little to no technical information on biodiesel from algal oil, so essentially the potential properties need to be estimated from the fatty acid profiles and data of what's out there, and that's why we also had data, for example, the C20:4, C22:6 I presented. So next slide, please. Many of those profiles contain high amounts of saturated and polyunsaturated fatty acids simultaneously. Point out icosapentaenoic and docosahexaenoic can be found in some algal oils. On the other hand, palmitic acid, probably the most common fatty acid in algal oils. So they might also, let's say, present cold flow properties if you want to make a biodiesel. Point out there are some exceptions. Next slide, please. The cetane numbers of most algal biodiesel will likely be the lower to mid 40s, considering their fatty acid profiles. So not all will meet the ASTM E6751 specification, and most will probably not meet the EN 14214. Kinematic viscosity will probably be 3.0 to 4.0. A few of them might actually fall below the lower limit in EN 14214. Oxidative stability is probably going to be a problem because of their high content of polyunsaturated fatty acids. Cold flow, just comparing here again the cloud point of palm oil around 16 degrees Celsius. That is about 44-45% C16.0. Soybean oil with these C16.0, C18.0 around 0 Celsius. Now, if we look at fatty acid profiles of algal oils, a lot of them are, let's say, 25-30% methyl palmitate. So, again, get an idea that's not going to be ideal for cold flow either. So, anyway, next slide, please. So, anyway, I think the high production potential has not been realized yet. So, on the other hand, many algal oil producers probably have not paid a lot of attention to the fact that even if they can make the fuel, that they will need a fuel that needs to compete in the marketplace. So it may actually some favorable properties. So. But there's probably a trade-off between that too. I mean, you'll have to have good properties and good production to make it really interesting. So, next slide. And pointing out that there are some algal oils that actually might have different profiles that are more favorable. For example, this species here, recorded in 2011, Triacylglycerol Feedstocks. That might actually be not too badly compared to many vegetable oils with its high content of oleic acid. So, anyway, I'm not going to get into these details now. So, next slide, please. If anybody's interested, I can say a few words about renewable diesel. Otherwise, I'll just skip over and then come to.
Can you talk about it?
Yeah. Okay. So. I was just thinking in the interest of time because it's 12 o'clock already and we're talking a while, so okay. A renewable diesel is essentially making hydrocarbons, for example, from a vegetable oil. It's closer in composition and properties to ultra-low sulfur petrodiesel, to what, let's say, engine manufacturers are used to, so I like it from that respect. Similar to biodiesel, no low sulfur and aromatics. Has higher, yes?
Without an ASTM definition, how can we know these things to be true?
Beg your pardon?
Without an ASTM definition.
Renewable diesel. Actually, I think there is something coming out from ASTM in that respect now.
We were just talking in the last session, there's no definition currently.
No. Well, getting to the definition, that's another matter. I mean, because other things. It would essentially have to meet the specifications in ASTM D975, which is the Petrodiesel standard. So,
okay.
now I remember John, do you remember something like that, reading something that there might be a separate ASTM specification
Yeah,
coming
we
out?
talked about that, but the basic point is that these fuels already meet D975.
They should,
so
I mean.
Why do you need a separate spec?
Well, I mean, the same as essentially, there are these specs now for essentially the neat biodiesel 6751 and the blend spec. I mean, generally,
And the new number one.
that's another issue, just a personal issue. I mean, I question the need for that. Essentially, if you have a petrodiesel that meets 975 and a biodiesel that meets 6751, why not be able to blend, but you do have a separate spec on them. So, yes.
I think the part of the issue is origination. I think there's several technologies to make renewable diesel, and sometimes the petrotreating will make the feedstock into syrup.
I mean, what the renewable diesel makers claim is that they make a fuel that is essentially even superior to the ULSD fuel. So it theoretically, it should not. You never know. That's right. But anyway, I think I've broke up in higher oxidative stability, and then the cold flow varies. Renewable diesel manufacturers say that they can kind of tailor the process to the desired cold flow. Obviously, in a lighter form, it would be of interest in aviation fuel because jet fuel is essentially just a lighter form of petroleum diesel fuel. The regulated exhaust emissions are likely reduced compared to regular petrodiesel, but not necessarily biodiesel. Actually, I point out the slides we had where we were comparing, for example, some fatty esters to hexadecane and dodecane. So that gives you some idea of how maybe renewable diesel might fare in terms of regulated exhaust emissions. Feedstock availability and cost issues are probably similar to biodiesel since it's essentially made from the same stuff. Lubricity is low, so because you're getting rid of the oxygen in the fuel. And then energy balance, or less favorable than biodiesel. Yes, question.
When you say low lubricity, are you saying lower than the ultra-low sulfur?
About the same.
About the same.
Yeah. Next slide. So, might be interesting to compare biodiesel and renewable diesel in terms of mass and energy balance. If you make, I'm going to look here at neat compounds again. If you make biodiesel, like methyl oleate from triolene, triglyceride or oleic acid, formulate, you get 100.5% mass balance. Actually, you get a little bit more out than you put in terms of mass. Because put it that way, you're adding it. In the biodiesel, you have an extra hydrogen compared to the triglyceride. Now, if you're using renewable diesel, making a decane from triolene, which would be the kind of the ideal product you make, you'll see you get about 81.5% mass balance because the oxygenated moiety goes off as CO2. Co-product otherwise is propane compared to the glycerol with biodiesel. So anyway, that gives about an 81.5% mass balance, but actually it has a somewhat higher energy content because it's a pure hydrocarbon. You can say anything that contains oxygen in a molecule is already kind of partially combusted. That's why biodiesel, you could say, is already partially combusted. It contains oxygen. Its energy content is a little bit lower, so you'll find that renewable diesel has a little bit higher energy content. Now, of course, what does that tell us too? Obviously, a product that has a higher energy content than its starting material means the energy has to come from somewhere. That means it comes from the process you put into making this stuff. So essentially, it absorbs energy, to put it that way, absorbs energy from the process it's made with and stores it. And that's why it has energy content. That's why, obviously, the process of making renewable diesel will require more energy than making biodiesel. Next slide. So anyway, to evaluate those, maybe do them where it's most appropriate to contain concerning properties. A biodiesel for ground applications, or you can utilize some other environmental benefits like exhaust emissions, biodegradability, safer handling. Renewable diesel in terms of its advantages for cold flow, it has a lighter form for aviation applitions. I also point out that the energy balance, I talked about in a slide or two ago, might be of that interest for aviation applications because there's really no viable alternative aviation fuel out there. So you might actually consider sacrificing some energy just for the sake of having that kind of fuel. That's another matter. So anyway, next slide. So, like I said, both of them are affected by the feedstock issue, fuel property issues. I talked about them a little bit. Co-products, I think some people have said that, it's so onerous to get glycerol when you make biodiesel because, what are you going to do with this stuff? But otherwise, this with biodiesel, you get green glycerol. Why do you want to go back and make glycerol petrochemically from propene if you can get it green when making biodiesel? So, my personal opinion, I think glycerol is definitely preferable over propane. Otherwise, it's probably a complex issue. There are advantages and disadvantages to both approaches. And next slide. And going back to biodiesel, I think that generally long-term biodiesel with improved properties will be needed to take advantage of its benefits. And sometimes incentives might not suffice if properties do not meet market demands. And the feedstocks with higher supply potential, for example, algae, will need to address that too. Next slide, please. That's actually my last slide. But going back to Rudolf Diesel, kind of closing the circle with his publication from 1912. Thank you for your attention, and I'm finally done.